Hello everyone, this is Pure Mathematics Chapter 2. In this video, we are going to discuss about the section 2.8, which is conversion between exponential and logarithmic forms. So before going to the conversions, we have to observe that the logarithmic function and the exponential function are inverses of each other. That is, if fx is equal to log x to the base a is the logarithmic function, then its inverse function is the exponential function. F inverse x is equal to a power x and vice versa. That means if logarithmic function is given as fx, its inverse function is exponential a power x. Similarly, if fx is given as a power x, then its inverse function will be logarithmic function. So logarithmic function and exponential function are inverses to each other. If one is given, the other one we can find. For example, let us take this. If fx is equal to log x to the base 5. This is a logarithmic function with the base 5. So the inverse function of this will be f inverse x is equal to 5 power x. So whatever the base in the logarithm, the same base we use here, but x will go to the powers because the exponential function is the inverse function of the logarithm. So if fx is equal to log x to the base 5, then its inverse function f inverse x is equal to 5 power x. So from logarithm, the inverse we are getting as exponential. The same way, if fx is equal to 10 power x, here this is a exponential function with the base 10. So for this, the inverse function will be a logarithmic function. So the inverse is f inverse x is equal to log x to the base 10. So whatever the base for the exponential, the same base we write logarithm. Only difference is here x is in the powers for the exponential, but here we write x as the logarithm of x to the base 10. X is in the domain for the inverse function. So for exponential, given exponential function fx is 10 power x, the inverse function is f inverse x is equal to log x to the base 10. From this, what we see, for any given exponential function, the inverse function is logarithmic function. Similarly, for any logarithmic function, the inverse function is exponential function with the same base. And here, one more observation, since f and f inverse, these two are inverses, if we take the composition of these two functions, you will get identity. So let us see here f circle f inverse at x. That is composition of f and f inverse. That is equal to f of f inverse x. First you find f inverse x, thereafter you apply f. And by definition here we have f inverse x is equal to a power x. So in place of f inverse x, if we put a power x, we will get f of a power x. Now the definition of f. The definition of fx is log x to the base a. Here f of a power x in place of x here a power x. Therefore by definition of f, this is logarithm of a power x to the base a. But using the logarithm properties, this power, in the powers we have x that can be written before logarithm. That is the property of logarithm. And anything in the power you can take it before and write. That is equal to therefore x times log a to the base a. And again using another property of logarithm, logarithm of any number to the same base is always 1. So this log a to the base a is 1. Therefore you will get x times 1, that is x. So finally what you are getting, this we use as a property, log a power x to the base a is always equal to x. Log a power x to the base a is equal to x. That means here a power x is exponential, logarithm is log function. So if we take logarithm and exponential together, that is the composition. Because one is inverse of other, we will get x as it is, because f and f inverse composition is always identity. So log of a power x to the base a is always x, and this is true for any base a. Same way, if we first take f inverse and thereafter f, like f inverse circle f at x is equal to f inverse of fx. So first we find fx. Fx is here log x to the base a. Now you find f inverse. By definition, f inverse x is equal to a power x. So f inverse of this inside bracket is log ax to the base a. Therefore f inverse of this in place of x log x to the base a, if we put, that is equal to a power log x to the base a. In place of x, here we have log x to the base a. Therefore this is equal to a power log x to the base a. And a power log x to the base a is equal to x. Why it is x? Because composition of f and f inverse is always identity. So f inverse circle f at x is equal to x. So finally we are getting x. So this can be used as a property. A power log x to the base a is always x. So first you apply logarithm, thereafter exponential with the same base, then the value is x. Here first you apply exponential, thereafter logarithm. If the base is same, then the value is x. So these are the two properties. Again we will see these properties in the examples. We'll go to the next slide. So these are some important notes. The first one is b power c equal to a is equivalent to log a to the base b equal to c. This is repeatedly we are using. So from exponential we are writing logarithm. So if you observe here, b power c, b is in the base and c is in the power, and the value of this is equal to a. This is exponential. Now when we are writing the logarithm to the a with the base b is equal to c. So here for exponential, a is the value and b is the base to the power of c. The same we can write it as logarithm of a, base here b, here also the logarithm also with the same base, but the value will be now c. So here the power will be the value of the logarithm. So vice versa. So here the value a will be in the domain of logarithm here. That is the range. Here a is in the range for the exponential, whereas in logarithm it is in the domain. Similarly here c is in the domain. When it comes to logarithm, it is in the range. So how to remember easily? Whatever we have base in the exponential will be same there in the logarithm, the same base. Only difference is a and c will be interchanged. Here c in the domain, here c in the range. Here a in the range, here a in the domain. So once you understand this relation between exponential and logarithm, we can write whenever an exponential is given equivalent logarithmic form. Similarly, whenever logarithmic is given, we can write the equivalent exponential. So to have, let us look at example for this. Here we have 5 power 2 equal to 25. We know this. 5 square is always equal to 25. This is a exponential equation. For this, what is the equivalent logarithm? Logarithm of 25. So here the exponentially with the base 5 and 2 is in the domain like. And whereas when it comes to logarithm, now logarithm is applied to what? 25, and to the base 5 will be equal to 2. The value will be 2 now. So what is the equivalent of 5 power 2 equal 25 is log 25 to the base 5 is equal to 2. The value is now 2. Similarly, we know 2 power 3 is equal to 8. 2 times 2 times 2 is always equal to 8. This is the exponential equation. So for this, the equivalent logarithm we can write. So logarithm of 8 to the base 2. Log of 8. We apply logarithm here to 8. So logarithm of 8 to the same base. What is the base here? 2. Here the same base will take for logarithm. Logarithm of 8 to the base 2 is equal to 3. So we have to repeatedly use this equivalent condition that whenever exponential is given, you can write logarithm. Same way, whenever logarithm is given, you can write exponent. Now the second note you can make, if y is equal to ln x, ln means logarithm to the base e. If the base is e, we call it as ln. Therefore, x will be equal to e power y. The base is e, so the same base we write as exponent. So x is equal to e power y. So whenever y equal to ln x, we can say x is e power y. The next one, y is log x to the base a. Base is a is given here. Therefore, what is the equivalent exponent? X is equal to a power y. The same base here, a, we will write in the exponent as base. So x is equal to a power y. And the next one, if two logarithms are equal with the same base, then the values where logarithm is applied is also equal. So here log x to the base a is equal to log y to the same base a. Then x is equal to y. Always if two logarithms are equal with the same base, then x is equal to y. The next property, if a power x is equal to a power y. So these two are two exponents with the same base, a and a here. Then the powers must be equal. So then you can equate x is equal to y. And the remaining two properties, earlier we have seen the composition of logarithm and exponential always identity. Here logarithm function log x to the base a, after that exponential function a. So a power log x to the base a is always equal to x. Same way log a power x to the base a is always equal to x. So here we applied first exponential, thereafter logarithm. In the first case, first we apply logarithm, thereafter exponential. So either way, the composition of exponential and logarithm is always identity. Therefore, this value will get x. So we use these also repeatedly when we are solving equations. We'll go to the next slide. So we'll see some more examples. Convert this 3 power 4 is equal to 81 in logarithmic form. So this is exponential form. 3 power 4 equal to 81, where 3 is the base. So when we are writing the logarithm, we have to take logarithm on the other side, because here this is exponent form. So when we are converting into logarithm, you have to take logarithm to 81. So log 81 to the base 3. Whatever the base in exponent, it will be the base for logarithm. So what is the equivalent logarithmic form? Log 81 to the base 3 is equal to 4. So that is the logarithmic form, equivalent logarithmic form of this 3 power 4 equal to 81. Similarly, we can see another 10 power 3 is equal to 1000. We know this 10 times 10 times 10 is 1000. So this is the exponent form. And using this exponential form, you can write logarithm. Same way, we have to apply logarithm to the right hand side, because the 10 power 3 is exponent and the value is 10,000. And now logarithm of 1000, 10 power 3 is 1000. Now logarithm of 1000 to the base 10 is equal to 3. So what is the equivalent form to this one? Logarithmic form of this is logarithm of 1000 to the base 10 is equal to 3. Now another example. Now logarithm is given, log 32 to the base 2 equal to 5. You have to convert this into exponential form. Here base is 2, logarithm of 32 to the base 2. So the same base we use for exponential now. Therefore 32 is equal to 2 power 5. 32 is equal to 2 power 5. So that is the exponential form from this logarithm. So given any exponential, you can find logarithm, and given any logarithm, you can find exponential form. Now solving logarithmic equations. So we try to solve equations involving logarithms. Let us take this example. Solve for x, where log x to the base 5 plus log 7 to the base 5 is equal to log 21 to the base 5 using the laws of logarithmic rules. So both sides we have logarithm. So you have to simplify both sides into a single logarithm, then compare both logarithms. If both have the same base, then you can equate xy values as we have seen before. So take the left hand side here, log x to the base 5 plus log 7 to the base 5. So sum of two logarithms, and we know the property log x to the base a plus log y to the base a is log xy. When there is addition between logarithms, we can rewrite it as log xy. Log x plus log y is log xy. So here log x to the base 5 plus log 7 to the base 5 is nothing but log x7, x times 7 to the same base 5. And the right hand side is log 21 to the base 5 as it is. So this left hand side only we simplified. Sum of two logarithms we simplified into a single logarithm using the property log x plus log y is equal to log xy. When we write into a single logarithm, we multiply those two, x and 7. Log x into 7 to the base 5. Now both sides are logarithms with the same base 5, and here also 5. So you can equate x times 7 and 21 using the above properties. So if you look at this is the property we are using, log x to the base a is equal to log y to the base a, then x is equal to y. So using that property, both sides are logarithms with the same base 5. Therefore, 7x must be equal to 21. 7x is 21. From that, x is equal to 21 over 7. So if we divide 21 by 7, you will get 3. So the value of x is 3. Now we will go to the next example. Solve for x. Log x plus 3 to the base 5 is equal to 2. So if you see this equation, there is logarithm on the one side, only left hand side. On the right hand side, we don't have logarithm. So if both sides are having logarithm terms, then we can compare logarithms just like in the previous example. But here only one logarithm on the left hand side, no logarithm on the right hand side. In this case, we have to rewrite this equation as exponential form, in the exponential form. So log x plus 3 to the base 5 is equal to, can be rewritten as exponential form. X plus 3 is equal to 5 power 2. So this base 5 will go to the exponent now, exponential form base. So x plus 3 will be equal to 5 power 2. So that is x plus 3 is 5 power 2 is 25. Therefore x is equal to 25 minus 3. Taking this 3 other side, 25 minus 3. Therefore x is equal to 25 minus 3, which is 22. So you have to understand that if both sides we have logarithm, left hand side, right hand side, we have to compare the logarithms by making the left hand side into a single term, then compare the logarithms. If there is only one logarithm on one side, then we have to rewrite this one in the exponential form, then find the value of x. So let us take one more example. Here solving exponential equations involving two different bases. So if both bases are same in both right hand side and left hand side, we can simply equate the powers. But if we have two different bases, we cannot compare the powers. So in that case, we have to take logarithms. Let us see this example. Solve 2 power x minus 4 is equal to 3 power x. Here both are exponent form, but here the base is 2 in the first left hand side, and here the base is 3 on the right hand side. So as it is, you cannot equate the powers because the both bases are not the same. Bases are different here. Base is 2 here, base is 3 here. You cannot equate the powers. In this case, we have to make use of logarithms. So take logarithms both sides. Log of 2 power x minus 4 is equal to log of 3 power x. Just we apply logarithms on both sides. So then we use the property of logarithm. So when we are applying logarithm, whatever we have in the power, that will come before. We can write it as before. So log 2 power x minus 4 is nothing but x minus 4 comes before times log 2 is equal to, on the right hand side, again we have 3 power x, log 3 power x. Then this power can be rewritten before logarithm, and this is equal to x log 3. Now if we expand, if you distribute this one, x minus 4 times log 2 is same as x log 2 minus 4 log 2. Just distributing x log 2 minus 4 log 2 is equal to x log 3. X log 3. Then our aim is to find x. So take all x terms one side and the constant terms other side. Here we have x log 2 left hand side. Here x log 3. So take this x log 3 to the left hand side. Then x log 2 minus x log 3 is equal to take this minus 4 log 2 to the right hand side. 4 log 2 plus 4 log 2. We are doing collecting all x terms to one side and constants the other side. So here x log 2 left hand side already we have, and we are taking this x log 3 to x log 3 to the left hand side, so that x log 2 minus x log 3 is equal to 4 log 2. Taking this minus 4 log 2 to the right, we will get 4 log 2. And now from these x log 2 minus x log 3, if you take x as common, then you can write it as x times log 2 minus log 3 is equal to 4 log 2. Finally, you need x. So x is equal to 4 log 2 divided by log 2 minus log 3. Dividing this equation by log 2 minus log 3, we will get x is equal to 4 log 2 divided by log 2 minus log 3. And using calculator, this log 4 log 2 divided by log 2 minus log 3 is minus 6.838. You can verify this. Here the logarithm is always, nothing is there means base is 10. In the calculator also there is a button log, the letters log here, log button. So you can apply log to the log applied on 2, log 2, and then multiply with 4. And that value divided by log 2 minus log 3. Using calculator, you will get this x value. And there are some more problems in the exercise. You can try. Convert the following exponential form to logarithmic form, and similarly convert the logarithmic form to exponential. You have to try this during the live class. We can check again. I can explain 1 or 2 problems here again. Here 36 power 1 by 2 equal to x. So 36 is the base and the value is 6. Now if you are converting into logarithm, how we write this one? Logarithm is now applied to 6. Log 6 and to the base 36. So whatever the base in the exponent, the same will be there in the logarithm, the same base. So log 6 to the base 36 is equal to 1 by 2. That is the equivalent logarithmic form. Similarly here, logarithm we have to apply on 1 by 8. Log 1 by 8 to the base 2 is equal to minus 3. And here log 27 to the base 3 is equal to 3. Here log 64 to the base 4 is equal to 3. Here log 1 to the base 4 is equal to 0. And coming to the next one, logarithm is given. Log 8 to the base 2 is 3. So what is the equivalent exponent form? 8 is equal to 2 power 3. Whatever the base 2 in logarithm, it will be the base for exponential also. Therefore 8 is equal to 2 power 3. That is the exponential form. And here 1 is equal to 4 power 0. That is the exponential form. Here 10,000 is equal to 10 power 4. And here 27 is equal to 3 power 3. And for this problem 3 is equal to 9 power 1 by 2. And for this 81 equal to 3 power 4. So you also try to do this and check your answers. And any questions you can ask in the online class. And we have some more problems in solving the equations. So you can try to solve these equations here. 2 logarithms are there with the addition plus. So you can use the property log x plus log y is log xy. You have to multiply x and 9 and write as a single logarithm. Then both sides are logarithms. You can equate both logarithms and find the x value. Here also second problem the same, and the third problem is same, and fourth, and but from 5th, 6th and 7th, these three problems, we have only logarithm. We don't have on the right hand side logarithm, only one side we have logarithm. So we have to write the equivalent exponential form and then solve for x. So for 5, 6 and 7, write the equivalent exponential forms and then solve for x. In the same way, 8, 9 and 10, the right hand side is not there, the logarithm terms are not there, so we have to rewrite as exponential form. But before writing exponential form, this left hand side write as a single term. Two logarithms are there. Using the properties of logarithm, write as a single term in logarithm as a single term, then apply the exponential form and find the value of x. So this is the end of this video, which is about section 2.8.